I'll look into this because I know I've definitely messed this up before too, in the way I was looking at it.
Yeah, no, but I mean, that's true, because the octaves of 110 are going to be powered to 2 times 110. So 660 is not. Although but it will come up and even, we'll look at an example where we can know. So that, again, that's just kind of a rule of thumb, but nothing is set in stone as to even sounds better than odd. And in fact, there's a lot of misinformation about that. But I will show you some of the mathematics, or examples of mathematics. I don't go through the actual math. So the intermod distortion, leave harmonic distortion for the time being. Intermod distortion is when we've got 2 or more tones in a sum with a nonlinearity. And basically, whenever you do that, if you run 2 or more signals through nonlinearity, you get sum and difference tones, right? So you get, in addition to all the harmonics of F1 or all the harmonics of F2, you also get these sum and differences. So you get like F1 plus F2, F1 minus F2, 2F1 minus F2. What's the problem with those? Depending on what your tones in are, these ratios may or may not be musical, right? All the harmonic series are at least musical. They're overtones of some kind. But these may or may not be depending on the tone. So this is where, a dissonant interval going may be okay, clean, but a dissonant interval through distortion can really sound bad because the intermod products may get carried away. You can also have nonlinearity that leave the amplitude intact but delay the phase in a nonlinear fashion. Remember, whenever we talk about filters, we talk about linear phase filters, right? That's like the common type of filter you always talk about, linear phase filters. Well, what's good about linear phase filters? They have a constant group delay, right? So a constant group delay means all frequencies are delayed by the same amount relative to their starting phase. So that any waveform that goes in comes out looking similar. Whereas you can have something that have a nonlinear phase delay such that you may delay upper harmonics more than lower harmonics or vice versa. Now the interesting thing about this is we don't generally hear phase differences. Like you can take, you can take a Fourier series for a square wave, right? That's the fundamental plus a third times the third harmonic plus a fifth times the fifth harmonic, etc. And you sum them up and it comes out to something like a square wave. You can delay those phases by random amounts and listen to it, and it still sounds like the original square wave. You can really change the phase delay. We hear more of the power of what's in these things. We can't hear phase that well. Okay. So, all right, now I'm briefly going to talk about construction issues. So, because this is the kind of stuff that falls outside the realm of any other pedal. So, it doesn't have to do with whether it's time-based or amplitude-based or anything. So, let's talk about power, right? You look at power, you have a couple of things here. You got you got 9 volts, right? Typically, batteries, pedals run off of the 9 volt battery, right? And that's because you need more than a standard like AAA cell to get some nice power supply rails. 9 volts are good. They work with IC. They work with diodes. Gets everything up high, and you're not running something that needs 6 AA batteries. So that's what you need to get the 9 volts from the basic cell, right? So 9 volts work well. The other option is power supply. Now, the older DOD pedals use an 1/8" jack. It's shaped just like a 1/4 inch, but it's a lot smaller, and that's what they use for their power supply. Boss pedals and a lot of other companies have adopted the standard Boss design use what's called a coaxial power adapter, which, if you haven't seen it, looks like that, right? It's a pin inside a circle. So, the interesting thing about the Boss that's kind of a little annoying is they are tip negative drain positive. Why is that annoying?
Is it the other way with coaxes?
Right, and why is it usually the other way with other things?
Because they don't want the shield is the negative part of the coax, isn't it?
Yeah, you shield and more importantly the chassis, right? Because if you use something where the outside of the shield is tied directly to chassis via a metal connector, that's good because most circuits are negative ground. You've got some very famous pedals that are positive ground. The old electro-harmonics and the fuzz-based designs are positive ground. But by and large, most things are negative ground, right? So the problem with having your outer be positive is you have to use a plastic jack. Look at any Boss pedal, anything that uses the standard Boss connector, it's always got a plastic power jack. Or maybe it's positive ground, but that's right. Okay, so that's your power supply. Well, let's say you're using batteries again, right? You want to build something in so that your pedal's not always turned on. But you may or may not want to have, you don't necessarily want to include an extra power switch, right? That's extra components. So you want a simple way of incorporating a power switch into your design. Well, the common technique is to put a 3-conductor jack on the input. So like right now, the pedal's off. If I keep turning it on, it never turns on. And the reason why is, although there is a battery in here, there is a 3-conductor switch, a tip ring shield, right? It's a stereo switch. But the interesting thing so it's a very common jack on the input. But what they do is this goes out to the signal, right? This is your tip. Now you insert a mono connector into it, right? Your tip gets connected to the signal. Your shield is connected to ground. And then what they do is they run the negative part of the battery to the ring. So when there's nothing in here, this negative part of the battery is disconnected, it's not doing anything, the circuit's open. When you plug it in, instead of having a stereo where this would connect to a third conductor, it actually shorts to the shield, it shorts to ground, and so this section completes the circuit and turns on the pedal. So if I plug it into the input, the light lights up, it turns on. So that is like one of the most common things with most pedals is that you use a tip ring shield connector to gate the power. And the power supply may or may not go through that, depending on the pedal design. So that's a good thing to save batteries. Great idea. Okay, important things about pedals too. Input and output impedances, right? One of the things you probably learned in electronics, I remember this was my first pop quiz when I took electronics, and that was a lecture on input and output impedances. Typically, you want the highest input impedance you can get and the lowest output impedance, right? Because that way, you're not loading your source and you're driving your next sync even better. So pedals should be designed that way. They're not always. The real problem is if you look at some of the original pedals, like the Dunlop Crybaby and the Fuzz Face, they had a very low input impedance. And while the effect was turned on, it wasn't that big a deal because it was part of the sound. It loaded it, but it gave a good sound, so who cared? But when the effect was off, the problem was the loading was still there. And that low impedance loaded the guitar. Remember, the guitar has a very high source impedance. So it loaded the guitar down and caused undesirable effects went off. And the reason it did that is because it was using what was called a single-ended bypass. And a single-ended bypass is basically, if you've got some effects circuit, and you've got your input, you effectively split to your input and split to your bypass pad. And then your output is a switch. And you switch between the